So in this section I'm gonna go over section 3.3, which is derivatives of trig functions. And to do that, to prove actually those rules, we need some special limits. So we're always going back to limits, as you know. It's the most important concept in calculus. The first one is if you're doing the limit as theta goes to 0 of sine theta over theta, these two have to be the same, equals 1. Well, if you put a 0 in there for theta, you get sine 0. But how is this going to be 1? There's several ways of proving this. The easiest way for us at this point is do left limit and right limit. Do the table. So if you look at the table, if you key in y equals sine x over x, and then go to table, and then key in, as you're approaching 0 from the left, and then as you're approaching 0 from the right, so negative. I think we need to focus. So negative 0.001, negative 0.01, negative 0.1, and then from the right, 0.1, 0.01, 0.001. So you can see as you're approaching 0 from the left or from the right, you're getting close to 1. And why is this not focusing? That is weird. Right here, you dumb. Okay, that's better. Okay, so you can see that the limit of sine theta or sine x over x is 1. Also, if the limit of sine theta over theta is 1, then also the limit of its reciprocal is 1, right? Theta over sine theta is 1. And then in the same token, we could find the limit as theta goes to 0 of 1 minus cosine theta over theta, but this is going to be 0 if you do the table. And the opposite would be 0. So sometimes you're going to see theta, cosine theta minus 1. This is the opposite of that, right? Which is, if 0 is for the original, then the opposite of 0 is going to be 0. Okay, so for example, just to practice these two rules, 46, page 198, if you're doing the limit as x goes to 0 of sine x over sine pi x. The first thing I would do is put a 0 there, but if I put a 0, I get 0 over 0, so well. Since I have sine x, so I need sine x over x. So if I'm dividing yx, then I gotta times yx. And that's what I have here. So I multiply divided by x, and I cut the original problem right there. Now this is going to be 1 if x goes to 0. For these to match, it's basically sine u over u as u goes to 0. Okay, it doesn't have to be x, any variable, as long as these two match, and this has to be 0. Okay, approaching 0. So if you pi x here, you need a pi there. If you're timesing by pi, then you need to divide by pi, okay? Which is a constant, so we can pull the constant out. So it's 1 over pi times 1, and that's also a 1, because the limit of pi over sine pi x is also 1, and your answer is 1 over pi. So you gotta be a little clever with those problems. Number 50, page 199. The limit as x goes to 0 of 1 minus secant x over 2x. Well, if we put a 0 in there, it's 1 minus secant 0 is 1 over cosine 0, which is 1, over 2 times 0, we get 0 over 0, no luck. So we're going to work it out. Since secant is 1 over cosine, we have no choice but to work it out over 2x. And now this would be so you need to times this by cosine, so it would be cosine x minus 1 over 2x cosine x. The 2 will come out because it's a constant, so it's a 1/2 limit as x goes to 0 of cosine x minus 1 over x, and then times the limit. So if we take that out, we have then 1 over cosine x. That's a 0, and that's a 1, and times 1/2, so the answer is 0. One more, and then we'll get to the derivative of trig functions, which is the topic that we're discussing in this section. Limit as x goes to 0 of cosecant x times sine of sine x. So basically cosecant 0 is 1 over sine 0, good luck, and then that's sine of 0, which is 0 times 1 over infinity. Okay, so basically we can write this as cosecant, which is 1 over sine. This is 1 over sine, so we would have sine of sine x over sine x, which looks like the rule that we're talking about, which looks like sine of u over u, if u equals sine x, okay? Sine of u over u, so it's sine over u. Now if u equals sine x, and as x goes to 0, then u is also sine of 0, which is also 0, okay? So this is the limit as u goes to 0, which is 1. So sometimes you have to go out of the box to do this kind of stuff. So now to the trig function derivatives. The first one is f of x equals sine x, then its derivative is cosine x. And again, to see this, I'll just show you this proof. So if f of x equals sine x, its derivative using limit, of course, is the limit h goes to 0, f of x plus h minus f of x over h. You know, I do ask proofs on the test only for extra credit, so watch out for that. F of x plus h is sine of x plus h. F of x is sine x over h. But from trig, you know, you have all the trig rules in the handout. If you have sine of a plus b, it's sine a cosine b plus cosine a sine b. So sine of x plus h, sine x cosine h plus cosine x sine h. And then we bring the minus sine x over h. And you will see now how important these rules that we did about limits are. So if you pull these two together, they have a common factor of sine x. So we have sine x cosine h minus 1 over h plus this is cosine x sine h over h. And if we split up the limit, remember h is what's going to 0 here, not x. So x sine x can be brought out, and then limit as h goes to 0 of this is 0. That's one of the rules that we just talked about. Cosine x can be brought. Limit of sine h over h is 1, so 0 plus cosine x is cosine x, and derivative of sine is cosine. Same token, we can prove derivative of cosine is negative sine. So rule number 2, derivative of cosine is negative sine. Let's look at some examples. Page 197. Y equals sine theta cosine theta. So it's derivative using the product rule. We fix, this is f times g. So we fix f times derivative of g plus fix g times derivative of f, derivative of the first. So sine theta, derivative of cosine is negative sine. Cosine theta, derivative of sine is cosine. So we get negative sine square theta plus cosine square theta, which we know it's cosine of 2 theta. And then derivative of tangent. Again, this is easier to prove because tangent is sine over cosine. So to prove this, we use the quotient rule, okay? And it's gonna give us secant square x. Derivative of cotangent, again we do quotient rule because the cotangent is sine over cosine, which would be cosecant square x. Derivative of secant, to prove it, we can write it as 1 over cosine and use the quotient rule. Secant x tangent x. And finally, derivative of, and you need to memorize these, cosecant x is negative cosecant x cotangent x. Okay, so number 4, page 197. 4, page 197. So we have y equals 2 secant x minus cosecant x. Derivative, again, that's a constant, we pull it out. Derivative of secant is secant tangent. And derivative of cosecant is negative cosecant x cotangent x. So this would be 2 secant x tangent x. Now two negatives make a positive, cosecant x cotangent x. 18 from page 197. Now we have to use the quotient rule because this is sine t over 1 plus tangent t. So derivative would be, we fix the bottom, times derivative of the top minus top derivative of the bottom over the bottom square. So 1 plus tangent times derivative of sine, which is cosine, minus sine, derivative of 1 is 0, derivative of tangent is sin square over 1 plus tangent t. So now we can work it out, distribute cosine, so it would be cosine t plus tangent times cosine. Remember tangent is sine over cosine, so that's sine, minus sine times secant square all over 1 plus tangent t square. Okay. Number 30, page 198. Page 198. It says equation of tangent line to the curve at the given point. So they want equation of the tangent line. Same concept but different problem. At pi negative 1. So y minus negative 1 equals m x minus pi. To find m, we gotta do derivative using quotient rule and using derivative of sine and cosine. So bottom, derivative of the top, derivative 1 plus sine is cosine, minus top, derivative of cosine is negative sine over the bottom square. So we get cosine square x. Now if we pull this and put it up here, it will be plus sine, so plus sine square x, which is this, this is a 1, so it's 1 plus sine x over cosine square x. M, so at the point pi negative 1, make the slope of the tangent line to the curve at that point, but we just plug in the pi, sine pi over cosine pi square. Sine pi is 0, cosine pi is negative 1. When you square it, it's 1, so the slope is 1. And now you go back, plug it in there, and you get your answer. Okay. Number 40, page 198. It says for what value of x or values of x does the graph has a horizontal tangent? Remember, horizontal tangent is when the slope is 0, so f prime of x equals 0. Using the product rule, you fix f times derivative of g. Derivative of cosine is negative sine. You fix g, derivative of e to the x equals 0. We can pull out e to the x. So we know e to the x is never 0, it's positive. So this is going to be 0 when sine x equals cosine x. And this is, if you look at the unit circle, this is when x equals pi over 4. And then 5 pi over 4, plus or minus, and so on. Okay. Now I'll look at 64, page 199, and that will be it for this section. 64, page 199. It says evaluate limit as x goes to infinity of x sine 1 over x. Well, we know the limit as u goes to 0, sine u over u is 1. This is close to that, but it's not the same. If we put infinity, that's infinity sine of 0, infinity times 0, which is God knows what. So if we need sine u, right? So if we let 1 over x equal u, then that means if u is the reciprocal of x, then x is the reciprocal of u. So x is 1 over u. So we will have 1 over u times sine of u, which is exactly what we want. Now we need u to be 0. When x is infinity, 1 over infinity is 0, so u is 0. Perfect. And that's going to give me the answer, which is 1. If you look at part B, evaluate limit as x goes to 0 of x sine 1 over x. Now x is going to 0, same problem but different limit. X sine of 1 over x. Well, for this one, I want to do what we know about the sandwich theorem. Sine of 1 over x is between negative 1 and 1. And we need to times by x. So if we times everything by x, we get this, this, and that. When x goes to 0, this is 0, and this is 0, so this is 0. And that's if x is positive, meaning x goes to 0 plus. You can do the same thing for x going to 0 minus. Look at my notes. Okay, and that's it for 3.3.